Okay, so we're moving on to part 2 of deriving the C4h character table. And where we left off was this conundrum where we got really far, we got this character table is looking good, but we're violating the character table rules because we had 8 classes and only 6 vectors. And furthermore, and we know that the number of irreducible representations or vectors has to equal the number of classes in the character table. So 8 doesn't equal 6, so that's bad. And furthermore, we know that the sum of the squares of the dimensionality, the character under the identity, has to equal the order of the point group, or the total symmetry operations, total number of symmetry operations in the point group, which is equal to 8. And that's not true because 1 squared plus 1 squared plus 2 squared plus 2 squared plus 1 squared plus 1 squared doesn't equal 8. Okay, the asymmetry operations. So how are we going to fix this? We are going to cross these out. Okay, and for each one of these, I'm going to just cross out this one first, EU, but we're going to cross out EG. And for both of these, we're going to break them up into 2 components with individual vectors. So in the end, we're going to end up with 8 ones, 1, 1, 1, 1, 1, 1, 1, 1, 8 vectors and 8 classes. That's going to be following our rule. And furthermore, 1 squared plus 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 1 squared is going to be equal to 8. So our character table rules will therefore be in place. And the problem with this is that there is no real functions that transform like this. You know, we tested these linear and quadratic functions. We didn't get this. We naturally got out with these 2 functions, these vectors that were actually linear combinations of 2 complex functions. Okay, functions that had imaginary components. So the easiest way to derive these is actually to start testing complex functions, okay, that will add up to give you back these functions, okay? And so one way that you can think about this is, so, and just for sake of space, I'm going to erase this one. We'll do this one later in the video. But first, we're going to start out with EU. And so, you know, you can think about this. This is x and y. And so what if we think about the function x plus iy? If we broke this up into x plus iy and x plus x minus iy, it's what we call the complex conjugate, we could get something that looks very similar to x, right? And so that is what we're going to test. We're actually going to test the function x plus iy. And there's different ways you can do this, similar functions you can test, but this is what we're going to do for this video. I'm just going to bring these columns down, and we're going to see what happens with this kind of crazy complex function. So just treat it like any other function. You take the identity operation, what happens to x plus iy? It goes to x plus iy. Of course, anything that we do identity to, it goes to itself. What about C4? Well, what's x plus iy going to go to? We know that x went to y when we did this, right? And when we did a C4 on y, y went to negative x. So we're going to get y minus ix, right? Because y went to negative x. And now we can see what this is equal to. And it's actually going to be equal to x plus iy whole quantity times I. Close to that, right? It's going to be negative I. So you have to start thinking about factoring out i's and negative i's. Well, why does that work? We can refoil this out. We get this term here is going to be I squared minus I squared y, right? Minus ix. Well, what's I? I is square root of negative 1. What's I squared? Therefore, negative 1. So what's negative I squared? 1. So this just equals y minus ix, which is exactly what we wanted. So we proved that actually x plus iy with C4 is an eigenfunction. It goes into something times itself, and so it indeed can stay as a single dimensional component here. It doesn't transform with anything else, like how x and y transform together. And so then we can write the matrix that describes this transformation, right? It's going to be x plus iy times negative I is that's the matrix. That's the one-by-one matrix. So the character, just like we were always doing in the first part of the video for all of these, the character of C4 here is going to be equal to negative I. And so now we put down a negative I, and that's our character. So we keep going here. We'll do a C2. C2, that's the next one, right? How does x plus iy go to? Well, we know in C2, x goes to negative x, and y goes to negative y. So what does this equal? X plus iy times I. No, that's not right. Times negative 1. Right? Just negative stuff. So this is going to get you a negative 1. So that wasn't too bad. So let's keep going. Whoops. C4h. C4h, x plus iy is going to go to, well, x spun all the way to negative y, and y spun all the way to x. So put in an x for where the y was, and this equals x plus iy times negative I. Why is that? Times, let's see, times I. Because if we factor this out, we get I squared y, well, I squared is negative 1. So we'll get back negative y, and then we get I times x, so plus ix. So our character here is just going to be I. Okay, and then for sigma h, what happens? Well, in sigma h, remember, x and y just went to the same thing because the sigma h is in the xy plane. So x plus iy is just going to go to x plus iy. We're going to get a value of 1. What about S4h? Well, remember S4h, just the same as C4h, sigma h. Sigma h we just established did nothing, so it's going to do the same thing as C4h. So we're going to get negative I. And then inversion takes x plus iy, and x goes to negative x, x, y, z, x comma y comma z goes to negative x, negative y, negative z, minus iy. So that's just the negative of what we started with. So the value there is negative 1, right? Just like C2. And then our last one here is S4. Well, S4 is C4 times sigma h. Sigma h we established didn't do anything. So we had a C4, so it's going to be same character C4, which is negative I. And I think I made a mistake here before when I said same character as C4h, right? For S4h, sigma h did nothing. So this should be a positive I. I just read the wrong value there. All right, and so what we have to do next is we have to figure out the other component here. And this ends up actually being very straightforward because we broke this up, and so we know 1 plus 1 has to equal 2. Something plus negative I has to equal 0. Well, that's going to be positive I. Something plus negative 1 has to equal negative 2. It's negative 1. Something plus I has to equal 0. That's negative I. Something plus 1 has to equal 2. That's 1. Something plus I has to equal 0. It's negative I. You start seeing patterns here. Something plus negative 1 has to equal negative 2. That's negative 1. Something plus I has to equal 0. That's positive I. And so that is exactly how you break up this EU vector into imaginary components. And And we did that by seeing how this function x plus iy transformed. And why did we choose that x plus y function? Well, we chose it because we started with, the aggregate EU, that was wrong. We knew x and y transformed as that. So we're looking for like something that was related to that function. And so we can do a similar thing for EG. EG, we know it transforms as xz and yz. Those transform together. So we can break that EG up. And so we'll do that once I finish erasing this. And then what we'll do is we'll use an imaginary function that has xz and yz in it. And so we can do, for example, so let's cross this one out. Instead, let's break this up into 1 and 1, the two components up of EG into 1 and 1. And in that way, we're going to be testing something like xz plus iyz, right? Something that's related to this. Basically, you're looking at two things that sum up and that get you something that's very similar to this, right? So with like the complex conjugate, xz minus iyz plus xz plus iyz. Okay, so how does the identity transform? Well, it transforms as 1. How does the C4 transform? Of now xz plus iyz. Well, this is going to be exactly how EU transformed, right? When we're testing x plus iy, except now we're multiplying each component by z. But we know that for C4, z didn't do anything. Z went to z both for x and y. So it's going to be the same thing. And same thing for C2. And same thing for C4-3, because z was a positive 1. So we're just copying it from above. But now, once we get to the negative 1 here, we're multiplying, so the sigma h, right? xz plus iyz, well, we know that the sigma h does nothing to x and y, but it turns z to negative z. So we got something like this, which is equal to negative quantity of what we started with. So we know the value is going to be negative 1. And another way of saying that is we could just take negative 1 and times it by this value, what we had before. So we get negative 1 and negative 1. And that makes us feel good because negative 1 plus negative 1 is negative 2. Here, we got another negative 1, and all these are negative 1s. So we're going to have to just take the negative of everything we see above. And this should all check. This should sum up to 0, what we started with. 1 plus 1 should equal to 2. Negative I plus I should equal to 0. Negative 1 plus negative 1 equals negative 2. I plus negative I equals 0. Negative 2 plus negative 1 plus negative 1 equals negative 2. Negative 1 plus I equals 0. 1 plus 1 equals 2. So it all makes sense. That's how we derive these sort of character tables with these imaginary components. The C4 ones that have imaginary are the simplest. They end up just being i's. They're not actually complex functions. They're just imaginary characters. But as you see, you can look at my C4h videos or some of my other videos where you get more complicated functions because you have off-axis rotations. So that gets quite complicated. But another thing to just tell you is all these character table, and we can look at the answer here, right? So we can look at this, what you get online. And you can see they ordered these things a little different. Like we had I and sigma h switched. It doesn't matter. We named the Mulliken symbols correctly. We got the correct functions. We got the right values. And another thing to say is that the character table rules apply for this character table function, right? For this character table, even though it has imaginary vectors. There are some, you want to consider individually the properties of these broken up components. There are special rule number 5, I call it. And you can look at my character table rule video to go over that, or I think it's the character, imaginary characters in character tables video. I go over that. But that's how you derive the C4H character table.